to catch on all background.
So here's some stuff about photoluminescence. I try to keep it short and sweet because there's a lot of math and confusing parts behind this topic. So photoluminescence, and the definition of it is that when matter, how light absorbs or emits from it. So absorption is when matter takes in a photon and then an electron is moved from its initial state to a higher energy level. And then spontaneous emission is matter releases a photon from it, and then it drops an electron from a higher energy level to a lower energy level. And then stimulated emission, it's like just our spontaneous emission, but instead of it just happening on its own, we have to then introduce a photon to the system to then it will then drop an electron from a higher to a lower energy level. And we can see here that our photon is labeled as h nu, or h bar nu, where h bar is h over 2 pi, and nu is our frequency. And then in our last part, we can see that we have a photon going by it, and then we're emitting another photon. Something to notice about in the stimulated emission is that these two photons, they'll have the same direction as each other, frequency and polarization. And polarization is that it'll have that same wave in, I guess, the same direction to each other. So such that if like you were looking at them side by side, it would be looking like it was like you'd only see one because they'd be perfectly covering the one behind it. And then to Einstein coefficients, they measure how likely a photon will be absorbed or emitted from the atom, where A is our spontaneous emission from going from our level from X and Y. B, that can either represent the absorption or that should say the absorption or the stimulated emission, or spontaneous and X. Probability from our transition from X to Y. G of X is our degeneracy, which is how many states could be in one level, and then F of XY is our oscillator strength. And then we can see here that from our continuous spectrum, our emission lines, that's like where at a certain frequency we're going to get a photon out of it. We can see at those frequencies we're receiving light, which is what we can see. Then later on, then we can see what our absorption lines are. So when our photon absorbed, we're not getting any light back, so that's why we don't have anything. And that's what I have.
Okay, please join me in thanking you. We've got introduction to spectroscopy. Any questions to William in the audience? Any questions to William from online? Any questions in the chat line?
All right, I guess. So you have oscillator strength there. What would, well, I guess what's a good way to describe oscillator strength?
I'm not sure exactly what this oscillator strength is. My initial thought would be, since the light we're dealing with is a wave, would be some sort of strength of our photon or something related to that. My initial thought.
And what is your good memories of the talk by Joseph last time, or maybe 2 times ago?
that I'm not sure of.
Just ask him, maybe he will help.
Yeah, so the oscillator strength is related directly, like through these constants, basically, to the probability that a photon will undergo that transition. So I guess from Will's equations here, we can see that there's like a few other constants that come into play, or a few other variables, I should say, like the frequency and the degeneracy. But like the main driver of it is the oscillator strength, which measures kind of like an overlap almost between two different like states. So if they have a high overlap, they have a high probability of transferring.
One thing that I would like to mention that confused me at first is that our E squared is the charge of an electron and not Euler's number squared. That's something that
What?
our E squared is the charge of an electron and not Euler's number, which confused me for a little bit.
Yeah. So like Dr. Killen said, we're just going to continue talking about photoluminescence. So kind of the main idea here is basically looking at how charge will relax and how the holes, I guess mostly just the excited electron will relax, and the probabilities associated with that. So first we have to worry about when that relaxation is actually going to emit a photon, or radiative recombination. From Will's presentation, we can easily tell that the rate that this will emit is just going to be the Einstein coefficient. And we're just going to relabel that as Kr. And then also here's the equation for the oscillator strength, in case you want the equation. To simply just get the value of the oscillator strength, we can run the oscillator strength file, which is the same process we would do when we're calculating the absorption spectra. And that will give us a big oscillator strength file, which will tell us this number for all combinations of bands that we're concerned about. Here we can also see different route commands that we can do on that oscillator strength file to get the different oscillator strengths that we might worry about. So we have oscillations between two excited states or intra-conduction band transitions. Same thing for the valence band transitions. And then we also have interband transitions. So basically going from an excited state to a relaxed state, I guess. And down below, we can see what one line of the oscillator strength file is going to look like. The two values that we're really concerned with are the oscillator strength and the transition energy, which both show up in our calculation of the radiative emission rate. The other pathway that charge can relax is going to be through non-radiative. And the way it will lose energy, instead of is through a photon, is through a phonon, or just heat that gets released into the rest of the system. And this is what we were calculating before when we were calculating the Redfield tensor. And so it will follow the exact same process that we did before, where we'll just use the autocorrelation functions and get the triple R matrix. And that's going to be approximately equal to the non-radiative rate. And just for an example, down below, I did this calculation for one of my models for the HOMO-LUMO transition. And when you run the correlation MATLAB script, the output in the triple R matrix is going to be inverse femtoseconds. In case you need to convert that to anything else. Combining those two rates, we're going to be able to get this photoluminescence quantum yield, which is a lot of words, but basically all it's saying is how many photons are emitted as a fraction of how many photons are absorbed. The big assumption that we make when we're calculating this is called Kasha's rule, which down in the bottom corner is a good kind of explanation of it. We assume that if you have an electron go to a very high excited state, far above LUMO, that it will descend to the LUMO state just releasing phonons, so non-radiatively. And then the only transition that will release a photon is between the LUMO and the HOMO. This doesn't happen all the time, which I'll talk about in a second. But this will greatly simplify this equation over to the left into what it is. If you are concerned about photon emission from higher excited states, this equation will become much more complex. As an example of some of these values, you can see down in the corner that I calculated for a few of my models. The first model has about a 55% quantum yield, so about half of the photons that are excited, or half of the electrons that are excited will release another photon. And as defects are added into it, COH and SiOC, that quantum yield goes down by quite a bit. So we also have some exceptions to Kasha's rule that we have to worry about. And I basically outlined basically how we would get these exceptions, but basically what it's playing with is if you want to adjust what KR, KN are in order to get emission from a different level. So for example, if you have a bunch of high excited states even further above LUMO, they'll have a low overlap between LUMO and those higher excited states. So those electrons won't get a chance to fall down to LUMO. And instead what they might do is basically fall all the way down from a high excited state down to HOMO and release a photon that way. And so through like these two sorts of exceptions, we could get luminescence from different states and different energies than just the HOMO-LUMO gap. So that is something to pay attention to if you have like an odd band energy diagram, I guess. That is what I have so far.
Okay, question. Thanks. Any questions? Okay.
What is a phonon?
So the phonon is just a like discrete it's kind of like a photon, except instead of releasing into like space, it's just released into the surrounding atoms as heat. So it'll just vibrate all of the atoms next to it.
So it's really just energy being released?
Yes, into kinetic energy. Yep, okay.
Quantum of sound?
Yeah, that would be a good way to put it.
How do you calculate KR?
The K, so KR will be calculated through the Einstein coefficient that we were just talking about with Will before, which will involve the transition energy between these two states and the degeneracy, as well as the oscillator strength. The KNR, so the non-radiative, would be calculated through the non-adiabatic couplings that we were doing, calculated on the Redfield tensor width, and then just looking at the indices of that matrix, that would tell you the rate between those two states.
Why not choose when you HOMO to LUMO plus N transition? Why not LUMO minus N?
Like in this example, why I chose the HOMO-LUMO.
At last. Yeah, why you are concerned on HOMO to LUMO plus N?
Oh, yes. So here what I was trying to show was that the Kasha's rule, we're not always going to get photons only emitted from the HOMO-LUMO transition. We might get photons emitted from a HOMO to LUMO plus 5 or something like that. So I guess like a good example, a better example is this one off to the right, where the LUMO is very close in energy to all of these higher excited states. So if you put a photon up to this higher excited state, and LUMO is going to have like a relatively low oscillator strength connection to HOMO, the KR is going to be low because its oscillator strength will be low. So then we will be about just as likely to see a transition from HOMO to LUMO releasing a photon, as well as like a higher LUMO state, releasing a photon. Yep.
Questions? Let's check if anyone asks you questions in the chat line.
Yeah, so do you have a question in the chat line? How to assess if Kasha or non-Kasha transitions play a more important role? Can it be done visually? I think that a visual way to do it, other than being able to look at, I think a good first step might be to look at the band energies, kind of like a diagram that I have here. Another good way to do it might be through the emission spectrum, like what Sarah was showing before, where instead of just emitting photons for the HOMO-LUMO transition, we also had different energies that were releasing photons. So I guess you could cross-reference the emission graph with its peaks to the transition energy between different pairings of HOMO and like LUMO plus N.
Is sufficient justification to compute spectra and waste them in your next presentation?
Thanks, so.
Next presenter is here, and she has a schedule conflict, so I will try to show her slide, but I cannot compete and present it as a solid talk. I will just focus on a couple of important things. And everyone is welcome to cooperate and be awesome. So it will be like not only here, but the whole club of computational chemists. So as we have heard from Joseph, it is quite beneficial to follow Sarah and compute photoluminescence spectrum. Those are based on our previous calculations of non-radiative relaxational dynamics. This is important. This is different from absorption spectra because the non-Kasha transitions may involve transitions between excited states. And in order to activate them, we need to populate orbitals that are not populated in the ground state. So we need to explore excited state dynamics as a prerequisite to compute photoluminescence. So one has, well, we all have a little code on the top of the quantum dynamics that just converts these dynamics into photoluminescence spectrum. And the aspect that Case was going to show, and I'll just surface her proxy, is just to focus on a couple of lines of the code that are responsible for this emission spectrum. So here are the standard things and the name of the code. I hope very much that next few speakers will cover these aspects in more details and from different points of view. So one of the important things that is needed for computing spectra is to import this 4-master optics file, which to my understanding contains oscillator strengths for all possible pairs of orbitals, including both from occupied to unoccupied, as well as occupied to occupied and unoccupied to unoccupied. And I believe on one of the previous talks, previous weeks, David was giving comment about structure and location of this file. Okay. So upon the dynamics is done, the data for occupations of the orbitals in the valence band and conduction band need to be merged with oscillator strengths in the right way. So here are a couple of lines of the code that do implement the equation on the top. So there were a lot of very important key concepts that Joseph has and given contributed to us. But there is one keyword that was implicit but not verbalized. When William was showing his diagrams with little levels, dots, and wavy lines, there was naturally assumed that emission happens from excited to brown, when population goes from higher energy level to lower energy level. If we believe in Boltzmann distribution, if we believe in thermodynamics and thermodynamic equilibrium, this should never happen. All occupations should go to the ground state, right? So the prerequisite for emission is in conflict with equilibrium thermodynamics. It should be a non-equilibrium state. So in a regular, stable thermodynamic equilibrium state, the populations are following, what's the right word for freshman chemistry? When all Fermi Pauli exclusion principle, up to Fermi level, everything is occupied, above everything is empty. Right? And now we need to violate this rule. We need to promote an electron higher up. We need to have a non-equilibrium. We need to have populations that are opposite to this natural arrangement of things. So it should be inverted. And the keyword is population inversion. The prerequisite for photoluminescence is population inversion. And we may set up scanning of the pairs of orbitals in such way so that we have one is always more senior than the other, to know who is senior, who is junior between orbitals. And then we can look if we ever have population, so let's open a green box, if you have population of the higher orbital bigger than population of the lower orbital. So if the subtraction is positive, it means we observe a population inversion. If it is negative, then we already arrange summation in such way that it will not be negative. We count on the possible contributions. So this little box bracket is population inversion. Okay, another prerequisite for photoluminescence is that it should match the emitted photon matching energy difference between initial and final states. So the frequency of emitted photon is equals to energy difference between initial and final. And the third prerequisite is that emitting pair of states should have non-zero fluctuator strands, should have non-zero transition dipole, and should be able to contribute. And then we scan over all the things. So populations are time dependent. Therefore, as we run through quantum dynamics, there are different pairs of orbitals that contribute or not contribute to the emission. And in this slide code, we have time dependent populations. We have the energy differences, and we have the oscillator strength that depends on two indices. When all these factors are combined, just basically multiplied, we implement resonance condition. Instead of delta function, we have Gaussian function, exponential, and the scanning over all possible emission frequencies is arranged as a contribution over all possible transitions is arranged as summation of different terms of this thing. So the resulting variable slice is a probability to emit a quantum at certain wavelengths at certain time. And if we scan through all possible time steps of our quantum dynamics, we will see that at each time slice, this probability is as function of frequency are different, right? So if we accumulate data into this array by adding more and more rows each time it comes through the cycle, it will be a matrix. And we'll forward to be a little less abstract, more practical. So the emission for certain systems can be even more pronounced of these non-Kasha transitions. You will get the Dinesh was asking. But the experiments that track time dependence of emission are cool and needed, but they are 10, 100 times more expensive. Much more typical ways to look on just whether it emits or not. So calorimeters are much like one can even buy it into a household. It's not more expensive than an average car. So one can integrate all these emission events over timeline and have this integrated emission. Let's go back to the line of code. So we do have this emission thing. One could make just summation along each line of this matrix, but since we have the time steps have different duration, one needs to arrange the varying increment of time into this integration. But as soon as this little convolution of two matrices is done, you have time-dependent emission. Another thing which is often shown doesn't have any relation to practical observables, but it does appeal to intuitive human thinking. So if we forget about this strange things about from non-Kasha emission, we will gap emission and just follow how the excited state of different energy cascading from more excited to lower excited. We can model this process just by arranging this population of electrons, population of holes, and the resonance condition, and just illustrate so that initial excitation at certain wavelengths, certain energy changes over time and drops to the form of dynamics of excited state. Again, it is not an experimental observable. It is not anything we compare. It's only a way to interpret how things are arranged. Okay. And practically, while studying certain materials, we may want to redo this calculation again and again with different initial conditions, because the emission properties do depend on excitation energy. Let's see if here shows here things together. Okay, the presentation is done. You can skip upload since the presenter is not on the meeting. But any questions, please go ahead and ask questions, and I'll either try to address them or we will postpone until he joins us next meeting and answer your questions. Yes,
Can you just say one more time on this slide, I guess, what the P is?
This one that is right now.
Like what it multiples. Is that like the power, the intensity?
Oh, but being here for excited state to appear at certain transition energy at a certain time. So in the code, it is encoded based on the name of one of my postdoctoral advisors. Either, I don't know, as a making fun of him or as a making tribute to him.
So hello everyone. I think everything is explained by Professor before, so I will explain the same thing. And the most important thing is that exciton, that in this case we study the dynamic of the exciton, that is the electron hole pair, and we need all the input files that we used for in the previous meeting, and here is the summary of that input files, and there are the 5 input files, and the RRR file, energy pop file, master optic file, band out file, and the MATLAB code. And we need to make sure that all the files have the same same number of lines. So we use in the same folder with the MATLAB code, and then we need open the MATLAB code, and we need to make some changes in the input parameters. So these are the some parameters that we need to change: time step, omin, and omax, and the homo, and then the z step that we can calculate from that we can see from the band out file, and then the z size from the postcard file. So these are the input parameters that we need to change, and this is the code that can be used to calculate the time integrated emission, and these are the equations that are explained by the professor, in which we use the one is time resolved emission and one is time integrated emission. So this is my model that I use for this calculation, that is the CNT with some defect, and that is the normal relaxation with initial condition, in which the yellow line represent the charge density of the photoexcited electron, and the dotted line represent the average energy of electron. And then this is the simple excitation of the excitation energy, how it changed with the time scale. So it is dynamic of the exciton energy dissipation with time, and the color range from the red to the blue, and red is the maximum population and blue is the zero population, and if it is the yellow, so it means it is in between the range. And this is the emission time resolved emission spectra, and this is the time integrated spectra. So we calculate the time resolved emission in the excited state, that is based on the presence of inverse occupation along the excited state trajectory and intensity of the oscillator strength. And the time integration is just simply the time resolved emission along the trajectory. So these are the results. That's it from my side. If you have any question, feel free to ask.
Okay, please join me in taking a part. So, any questions or suggestions? Like as a practical manual, is it clear? Every of us can repeat it. Amar, I do have a couple of suggestions rather than questions.
Okay.
So for this figure, would you be able to learn from Joseph and give a number? What is the photoluminescence quantum used for this model?
For this figure?
Yes. It's not available right as a number from this code. You need additional code that Joseph presented today.
Okay, maybe I missed that code, so I will go through that.
His presentation, maybe listen the recording and try to find quantum U.
Okay, yes.
Let's go to previous figure. Maybe Dr. Hunt has questions to it. So, from either fundamental or practical side. So while we are still thinking if there are more questions, let briefly. There are specific features of the geometry of your model. So can you please bring your marker, your cursor to the defect, to the small to this absorbed on the surface? Closer to the molecule on the model. Yes. So,
yes.
So there are two carbon-carbon bonds that define this model, right?
Yes.
So right now, these two bonds are arranged in parallel to the tube axis.
Yes.
Would you be able to place them perpendicular to the tube axis or at some other different angle?
Yes.
Okay. Yeah. So it would be of very big scientific interest to change the orientation of the attachment points and see how the spectra and quantum yield will change.
Okay. Yes.
So it was not a question; it was just suggestion how to.
Yes.
Any additional questions to Amara? Let's count down. Questions 1, questions 2, questions 3. Please join me in thanking Amara when you speak. Thank you.
Okay. So, I was just going to talk about time-dependent, time-resolved, and time-integrated. I found these cool figures that basically show we're taking slices of time-dependent emission spectra, certain wavelengths, integrating those to, just this time-resolved spectrum over here. I just showed the part of the code, I guess, that does this and what it relates to. Yeah, that's basically what I have for that. It's nothing we haven't already talked about, but also I found this, while I was doing research, I found this time slicing that they do. So they basically just overlay these emission spectra over one another at different times, and they do this for. They actually plot another figure from this. Basically, it says like how the intensity, I guess, changes over time. But they use this to explore like solvent relaxation. Now that affects the rate of these things and I guess charge transfer systems. So they looked at an intermolecular charge transfer system here, and they just looked at it all these different time slices. But that was basically all I had.
Okay, is it time to upload to Adam, right? Okay, let's take Adam. Any questions in the room? Any questions from online audience? Adam, do you see any questions in the chat line?
Oh yeah. Absolutely, yeah. Okay. Yeah, fluorescence, phosphorescence, and photoluminescence. Photoluminescence describes fluorescence, phosphorescence, and that that resonant photoluminescence that I think William described here. They're not equal. They're describing different processes. These are like slow releases. I guess they're not releases, but slow decays. Phosphorescence specifically describes entering or a decay from a triplet state, so that usually takes a bit longer, and so the emitted, I guess, wavelength of light is going to be a little bit longer than with fluorescence.
So fireflies, which sort of emission do they show?
I believe it's phosphorescence because it's so long-lived.
Okay. Can anyone compute phosphorescence without spin orbit coupling? Oh, let's make a vote. Who can compute phosphorescence without computationally without involving spin orbit coupling? No one is raising hands, which means it's likely impossible.
Yeah.
So if you got a connection to the next speaker, David, who will show that spin orbit coupling is more universal and will enable both fluorescence and phosphorescence if needed. Just I wouldn't say personal, practical question. Did you got couplings? Did you got input files to run this photoluminescence codes for your model? Or there are some technical difficulties?
I did get figures for it. I didn't see very much from them. If it runs, I'll show you.
Okay.
Okay, yeah. So
I think one needs to push space or any key once again.
Let's see.
So how do you interpret that TM is changing over time? You see this TM is raising in your command line.
Yeah, those are just the. Okay, so here we have it.
Ah, so you have everything, right?
I believe so, yeah.
So you have computed emission.
Yeah.
Okay, that's then a great talk with a practical component. You are just ready to combine these figures, describe them, and go to the next paper.
Maybe so. Maybe a bit more work, but.
Okay, I'm very happy to see it. Any questions to this little results? It looks like Honolulu emission is noticeable, right? So let's well, very soon, starting from the next week, we'll go to research updates. So probably this is already partially belongs to research update, but any questions to the protocol? Anyone wants to learn from Adam how to run, how to compute photoluminescence? Questions? Please join me in thanking Adam once again. Now the next speaker is Sarah. So her talk will give practical skills of computing photoluminescence for the models with explicit spin polarization, with unpaired spins. We will, after her talk, we will go back to background and ramp up to this level of development in a little more continuous way. Okay, Sarah, floor is yours.
Thank you, Dr. Killian. Hello, everyone.
So I'm going to briefly explain about how to generate the emission spectra for the spin polarized case. So as I talked, as I talked previous weeks, in order to run this MATLAB code, we need some files, including the RRR file, bound out diff, bound out some energy pop, formaster, and absolutely the MATLAB code. So as I mentioned previous week, we need to modify a bunch of numbers in the MATLAB code. We need to specify the number of HOMO, LUMO, the range of orbital that we want, the number of steps, as well as the cell size in the z direction, and of course the transition that we are interested in. In this case, we kind of sorted the always the strengths file and we are interested in the transitions with the highest oscillator. So after modifying the MATLAB code, if all process goes well with the MATLAB code, we ended up to some plots. So one of them is, as you can see in the left, the energy dissipation as a function of time and as a function of space in the right panel. Also, we can see the relaxation rate for the electron and holes. So electron is kind of showed by the yellowish color, and the hole by the bluish or purplish color. So next and final images or pictures that MATLAB plots for us are these three panels. As you can see from top left, this is the dissipation of excitation energy as a function of time, and also as well as on the top on the right, it is the emission spectra, and also time integrated emission in the below the time integrated emission. So you can see that each peak corresponds for a specific transition. So for my case, the highest intensity for the excitation energy corresponds to the LUMO to HOMO, and also we can modify this range of energy to our desired range of energy with just very simple. We need to just modify this part of the MATLAB code, which the A-axis, it's a MATLAB command that you will tell it that which range of x-axis and y-axis you are interested in. In this case, for the x minimum x, we want minus 3.03, and the maximum of the x axis as a 3 electron volt, and for the y-axis we wanted the range from starting from 0 to 7.3 electron volt. So I'm done. Thank you. Is there any question?
Please join me. Thank you, Sarah. So it was a record brief. Thank you. So any questions in the audience, online or in the chat line?
Which transition is below LUMO HOMO? Still there are some peaks.
Excuse me, Dr. King, can you repeat the question? I think Dr. Tapa is far away from microphone.
I still see some peaks below LUMO HOMO transition. What are those peaks?
You mean these peaks for this figure?
Below, yeah, that peak. Yes,
I'm not sure. We need to double check the O strength file and see which transition or correspond to this energy level. So I'm not sure from this case what are each peaks correspond to I think just these two are kind of more important for us, which was LUMO to HOMO, and this one LUMO plus 2 to HOMO.
Sorry,
So
I think what Dr. Sapa, what Dinesh is asking, just generally, qualitatively, how to interpret presence of optical signal below HOMO-LUMO gap. Not literally which individual, but generally, what is it?
Something like, for example, maybe it corresponds to LUMO minus something to HOMO, or so.
So let me reformulate the question. Those transitions below the gap, do they happen from between valence and conduction band, from valence to valence, from conduction to conduction, or like which of these three options?
Still, I'm not sure about the answer for this question.
Anyone wants to try? We will have several talks to focus. So let's mark these open questions for all of us, and try to get it from each next speaker.
Can I ask why we think the LUMO plus 2 to HOMO transition is so much more important than them, when the one that like 0.8 eV is like 2 orders of magnitude higher intensity?
Okay, let's maybe, Sarah, please prepare to answer a question of David, and I will contribute a little bit to the question of Dinesh.
Okay.
So, and Sarah, would you please go to the editing mode so that one can put a little annotation? Editing, exit the presentation mode and go to the editing mode.
Let's see.
Yeah, thank you. The question that Dinesh did ask is showing a conflict between intuitive thinking and objective calculations. So there is a process that one can agree that we go from higher excited to lower excited by scrolling several orbitals in valence band and conduction band, and then at the end we come to the HOMO-LUMO gap. So the HOMO-LUMO transition between valence and conduction band seems to be to have the lowest transition energy, right?
Yep.
Yes, agree. But we were in this little exercise. We were thinking that the light can be emitted only to ground state from an excited state. But in addition, there are processes of radiative transition between several excited states. So if you go between individual electronic orbitals radiative way, then the transition energies of this little processes will be below the gap. Sarah, would you approve?
Yeah.
Okay, so this question is done. Now let's return to the question by David.
So the question by David, why these two transitions are important. So the LUMO to HOMO is, as Dr. Klein said, I think we expected to have the lowest excitation energy and the highest intensity. So just we wanted to see that if we are right or wrong. So that LUMO to HOMO is for that. But LUMO plus 2 to HOMO. So for this one, actually, since we have for the in our paper we had a kind of a figure that has all 3 spin multiplicities on it. So this one is just for the n up down 1 or the low spin multiplicity. So I on that figure that all 3 were together. So we just showed this transition. I think we wanted to comparison it with the maybe the other 2 spin multiplicities. So I think the reason was that because of the comparison, but I'm not sure that if any other reason is there is any other reason for this one or no.
Are you satisfied with the answer? Sure. Okay, David is happy.
So I am going to talk about 2 more things that we can, observables we can examine in our calculations. So MDPL, which is the molecular dynamics photoluminescence, and photoluminescence quantum yield. So we're going to start with MDPL. So if we, with your spin orbit calculation, there is a code that is in the bin on NERSC, which is modified encoding off human. So it's this OS underscore PL underscore scripts. You're also going to need from your coupling calculations all the OS underscore strength underscore VC dot XXX files. So these are your files that show the oscillator strength along the trajectory, and specifically the ones along for interband. So if we open up this OS underscore PL script, you're going to see what we have over here. And if you look in the red box, I have the values. These are the values of X in the oscillator strength files that you have. So however many you have, you should fill in here. Depending on what V script you use, we also have to change this 4 in the %04G to 3, because that's setting it out to be 4 digits, and I think I'm the only one that uses code that sets it to 4 digits. So what this code does is it generates an oscillator strength file with just the homo-lumo transition through all of along your molecular dynamics trajectory. So to actually generate this spectra, once you have that oscillator strength file that was generated by the script in the last slide, you treat it just like how we treat absorption spectra. So you will plot it and you will get out a plot, which I did not include. I can probably add one quick.
Yeah, let's do it. In the same style as Adam. So I will cancel the session.
So if you look at this, this is the MDPL for a few of my structures that I used on my Sanibel poster. So if we look at them, part of the reason we're interested in this is it allows us to calculate the width of these so we can compare them to experimental spectra. So then moving on to the photoluminescence quantum yield, we have a MATLAB script that I wrote to calculate the photoluminescence quantum yield for spin orbit coupling. I wrote this based on some Excel sheets that Aaron sent me. So you need the energy pop for master optics and the RRR file. And then if you run this, it will calculate the PLQY based on the Redfield tensor and the Einstein coefficient of spontaneous emission. The major thing you would have to change probably these first three. Realistically, the two G's are going to be the same, but if you have a system that would require changing them, you would change it here. So this outputs these photoluminescent quantum yield values. So for this code, we use the average value for the near degenerate band gap transitions as our photoluminescence quantum yield, which is why we have 4 values here and then a final value. So we calculated for HOMO to LUMO plus 1, HOMO minus 1 to LUMO, HOMO minus 1 to LUMO plus 1. And then take the average of that value. And that's the end of my presentation.
Okay, with Jeremy, thank you, sir. Any questions in the room? How did you find the difference in PLQY?
So you need to examine if there's any degenerate states in your file. So due to the spin orbit, we basically end up with 2 degenerate states.
So what that file, it just looked like you have repeat lines?
What do you mean?
Or like, you said you look at the file, it's also it's degenerate. Would you just see?
Do you insert degeneracy manually or it automatically assess if any energy level is close enough?
We insert it, it's a variable we insert. So it's based on the value of energy and whether they're the same or pretty much the same. So all my values are less than a milli electron volt difference. Or some of them significantly less than a milli electron volts.
If one needs to compute photoluminescence not by MTPL but by Redfield approach, same as Sarah, Kia, Amara, are there any changes to the code, or you just modify the input parameters and use the same code? What do you mean? If you need to not keep width, but if you just need the photoluminescence, which you are not showing in this talk, not the quantum yield.
Oh, like the blue figures?
Yes. Does the way to compute blue figures similar but different from situation with single nodes?
Virtually identical.
Therefore, you skip it.
Yeah, basically.
Okay.
This is just from one of the other figures. It's virtually identical.
Okay. Yeah. Thank you. Okay. Let's check. Let's check if anyone asks you questions in the chat line. And Adam, please look at this question and think how you would answer it.
Aaron asks, is MDPL able to capture Frank Condon factors vibrational progressions?
It is a provocative question.
I hope so.
Let's give chance to Adam. Adam, would you like to just share your opinion to address this question?
Ooh,
I know it's a little too steep step to listen for new methods 4 minutes ago and now assess it and compare. But just your vision, how would this MTPL method do anything comparable to from quantum progression or very far, or do you see any connections? You see nothing, you can criticize that it is partial, just
yeah, I kind of can. I don't know exactly how to put it, but you have, the energy.
So what's the main condition to develop from quantum progression? And maybe you can even briefly remind it to those of us who want such a refresher. Like, how does one come to from quantum progression? Which conditions to nuclear degrees of freedom are important?
Vibrational states.
So vibrational, which means vibrations, interatomic distances, are they just point charges or something more than that?
I mean, there's something more than that.
Like you already answered. Sorry for making it as a little looking like exam, but you once answered one needs vibrational state. So instead of continuous exploration of different points on the potential energy surface, you are speaking of vibrational states.
Yeah.
So,
like of the, of the entire molecule, or of portions.
So vibrational motion should be classical or quantum in order to speak about from quantum factors.
Probably quantum.
Perfect. Yeah. Thank you. And what do you think about? Do not hesitate to be critical. What do you think about the MTPL method that David has presented? Does it have any quantization of positions of ions?
Not that I can see, no.
Like when we run molecular dynamics in computational chemistry software, do you have strict exact position of ions, or they all atoms are like cloud which is smeared over the whole space?
I believe they're clouds that just just gives them electronic structure, bases their motion on it.
Okay, thank you. David, would you like to continue the discussion and summarize? You have all information, and I have no doubts. You know that, right? Only a little exercise to verbalize things.
So I think that's most of the reason we were doing MTPL, wasn't it? Because we need to worry about it over the trajectory instead of just at a random fixed point that we picked or get picked.
Yes. So right now we are approaching to the real life and potential interaction with reviewers of works activity. So David is presenting situation from a constructive point of view, achieving good result. So in order to see how atomistic motion affects line width, this method is introduced. But if reviewers are trained to find any weaknesses, they will immediately tell any discussion of quantum factors is based on quantization of nuclear motion. If your nuclear motion is not quantized, it is not from quantum factor. And it will look like we are student and they are. So one needs to find what Aaron invites us to do is to find, he gives us a task to find a bridge, to find a connection, to say that on one hand we appreciate and that if nuclear degree of freedom are quantized, there is a progression that contributes to width of a line. On another hand, you can approximately get the same effect by scanning through whole amplitude of interatomic motions. Is it something what you wanted to say?
Yeah.
Aaron, would you like to summarize it in a better way? Did we perform a good try answering your question, and how would you answer yourself?
I guess I would hedge and say it captures some aspects that you would see with Frank Condon.
Okay.
And that we're dealing with solids and high temperatures, so it's experimentally those wouldn't be resolvable anyway, unless you were doing very specific types of or very specific experiments, like low temperature or something. So it could be like a homogeneous line width.
Mm-hmm. Many thanks, many thanks. So let me illustrate this discussion, and I think Adam will agree and appreciate it. So the Frank Condon progression, which Adam did compute in his fourth term, shows that either charge transfer or optical transitions do depend on energy offset and have a progression of peaks. When vibrational levels come of the initial and final state come into literal resonance. Adam, would you confirm that this figure looks similar to what you did in the past?
Yeah, it does. It looks like one of the figures.
Okay, thank you. And if one increases temperature, then through several mechanisms, the width of each individual peak will become broader, and several peaks originating from quantized nature of nuclear motion will start overlapping. So as temperature will increase, the system is coming to like quasi-classical regime, and the modeling of transitions with an account of this variety of transitions through classical mechanism will coincide better and better with quantum approach through Frank Condon progression. Aaron, would you take it as an improvement on our side?
I mean, I would buy it.
Okay, thank you. David, what do you think about another comment from Aaron?
Another aspect that is needed for Frank Condon is excited state potential energy surface here is only ground state. I would agree on both points.
Okay. So, any additional questions to David from the audience, from online audience, or from the chat line?